This video on the Matrox Rapixo FPGA development kit is part 2 of a series on the Vivado HLS design flow. We will create a new Vivado project and then add an IP repository to store the example processing units that we generated in part 1. Next, we will make a block design that includes the example PUs and generate a new firmware file. Finally, we test the new firmware on a Rapixo CXP Pro board. In part 1 of the HLS design flow video, we compiled each example PU and packaged the files in the format required by IP Integrator. To find the add constant IP, start from its project folder, then open Solution 1, Implementation, IP. Everything we need is in this zip file. To use the example PUs, we will create a new Vivado project. So first make a new folder for the project. In this folder, make a place to store the IP. We'll call it IP, but you can use any name. Now each processing unit needs its own subfolder. Here's one for add constant. For add constant, select everything in the zip file and copy it to its place in the IP repository. Now repeat that for the 4 main example PUs, and you should have a collection of IP like this. If you did not compile the examples yourself, you can copy the IP folder from this location in the FDK install directory. Now start Vivado and type the usual commands to create a new project in the folder where you put the IP. This is the base block design to which we want to add PUs, but first we have to tell Vivado where to find the PUs. To do this, we add an IP repository. In Settings, find the IP settings and expand them. Then choose Repository, and then click Add. Navigate to the IP folder you created earlier and press Select. Then press OK. We are now ready to add some processing units to the block design. Maximize the window to make it easier to work with the block design. You can also simplify the diagram by showing only the main interface connections. Now to add IP, press this button, search for HLS, and drag Add Constant onto the diagram. Then press Escape to remove that dialog box. We need to supply source stream for add constant and send the destination stream back to memory. We cannot use the existing DMA read and DMA write because they're already being used to implement a buffer copy. So let's add new transfer units. A DMA read and a DMA write. Now the stream output of DMA read can connect to the source stream of add constant, and the destination stream of add constant can be sent to DMA write. Make sure you use the stream ports, which are called AXI-S. The S is for stream. Now every block controlled by the host CPU has a register file port that must connect to AXI Reg Master on the CCU. You can recognize the register file ports as they are type AXI slave. To make the connections to AXI Reg Master, we will need 3 more ports on this interconnect block. Double-click, increase the number of master interfaces to 5. Then make the connections. The new DMA units must also connect to memory through their memory port. That means we'll need 2 more connections on this interconnect block. Now we can connect the memory ports. Note that this block design allows mbuff copy and add constant to run at the same time because each one has its own dedicated transfer units. If we add the remaining PUs in this way, the final design will have a lot of transfer units and take up a lot of space in the FPGA. In this case, we only want to test the examples one at a time, so a better design would allow sharing of the transfer units. Sharing transfer units, or TUs, requires software-controlled routing of data streams. So we'll add an Axi4 stream interconnect IP, which is basically a stream switch. Now we can delete the extra TUs and connect everything through the switch. Configure the switch for 2 inputs and 2 outputs, and also set the arbitration to 32 transfers. The arbitration setting is important as the default value of 1 gives poor performance. Now make the connections as follows. The stream from DMA read should be disconnected from DMA write, and instead it should enter the switch. Now one possible route from the switch is back to DMA write to implement the buffer copy. Another possible route out of the switch is to the input of add constant, and the output of add constant goes back to the switch. From there it can be routed to DMA write. This design can support mbuff copy or add constant and only uses 2 TUs. Now we'll add the other example PUs. Gain offset, convolve, and min-max. Note that min-max does not have an output stream, so the switch will need 2 more inputs and 3 more outputs. So let's add them. The switch can now supply the source stream of the other PUs, so connect them. And the PUs can send their outputs back to the switch. The only PU not fully connected is gain offset, which has 3 inputs, source, offset, and gain. The offset and gain input streams are needed at the same time as the source stream, so sharing a single DMA read is not possible. For gain offset, we must add 2 more DMA read units. Since they are dedicated to gain offset, we can connect them directly instead of going through the switch. They also need connections to memory. Everything also needs connections for the register file, so add more ports to the interconnect and make the connections. Let's make the diagram even bigger so it's a little easier to see. The design now looks complete, but we still have to connect the clock, reset, and interrupts. So let's make sure they are visible by pushing this button. Most blocks have a single clock and reset input, but the switch has 1 per port, and we have to connect them all. Note that IP Integrator offers to complete the connections for you through connection automation, but this is not compatible with the FDK, so do not try to use connection automation. To connect the clocks, start at the CCU, right-click and select Start Connection Mode. Then click once on all the unconnected clock ports. Press Escape to end connection mode. Now connect the CCU reset output to all the reset inputs using connection mode again. The remaining connections are the interrupts. All the transfer units should have the interrupt output connected, but processing units that produce an output stream normally do not need an interrupt. Note that the min-max PU has no output stream, and so does need its interrupt connecting. The number of interrupts needed will be 5 in total, so configure the CCU and make the connections. The block design is now complete, but we still need to assign some addresses, so select the Address Editor. Right-click and choose Assign Address for all the unmapped slave ports. The exact address range mapped is not important as long as there is no overlap, but a range of 4K is big enough and makes it easier to ensure no overlap. The design is now complete, so save it, then we can generate the bit stream. Vivado will run all the required steps and you can watch the progress in the Design Runs tab. After some time, typically 1 to 2 hours, the firmware file will be generated. We don't need to open the design, so press Cancel when prompted. Vivado has now generated the firmware. To find the firmware file, start in the project folder and navigate to Runs Implementation 1. Here is the firmware file. To update a Repixel board with the new firmware, start by copying it to the MIL firmware folder as explained in an earlier video. Here is the MIL firmware folder for the Repixel CXP. This is our custom firmware file, renamed to start with the letters FDK so that it takes priority over the standard firmware file. To trigger a firmware update, just start any MIL application. For example, we can use MIL config and navigate to the Repixel CXP board. The firmware updater indicates in red which board requires an update. Press Update and then OK. The update process first clears the Repixel flash memory and then writes the new firmware file. It takes a minute or two, so we'll speed this up. After the firmware is written to flash memory, it is automatically loaded into the FPGA. The board state will turn green when this is finished. However, if you have very old firmware, this last step is not supported and you will need to shut down the PC before using the new firmware. Now the new firmware is loaded, we can test the example PUs. Here in the examples folder, we'll start with add constant. In the header file, C2H-debug is currently defined, so the PU will be simulated. The processing takes over 200 milliseconds to run the simulation when the application is compiled in debug mode. It will be faster in release mode. Now comment out C2H-debug and recompile. Now when the program runs, it displays the same image as before and the same result, but the processing time is now much faster at 0.15 milliseconds. Note that the same validation that was done in simulation is now being done to check that the real PU is producing correct results, and we can see that the add constant PU is working as expected. We can now try some other examples, such as convolve. In the header file, C2H debug is commented out, so the real PU will be used. And the convolve PU is working as expected. If you have a Rapixo board in your computer, you can now test the other example PUs. Note that the destination buffer for a PU can optionally be in host memory, but only if you included that path in your block design. The firmware that we designed in this video did not include the required stream port on the CCU. If you want more practice with IP Integrator, you could add a stream port to the CCU so that an output stream from the switch can be sent directly to host memory. You could also redesign the firmware to allow multiple PUs to run in parallel. If you change FDK stream width to 128 in each PU's hardware.h file, you can generate PUs that use wider streams and process more pixels in parallel. For more information on how to write your own optimized HLSC code, see the video on creating a custom PU.